All right, so in this video here, we're going to talk about what happens when you're trying to graph a rational function and you factor your numerator and denominator, and it turns out that they have a factor in common that you can cancel out. Well, what ends up happening in that case is that instead of, remember when you factor the denominator, and if you haven't seen the other videos I did about rational functions and how to find the asymptotes and all that stuff, you should check those out because I'm going to use some of that information to explain this here. But if you recall, when you factor your denominator, any x values that make the denominator equal 0 are going to be vertical asymptotes. Right? The exception to that is if you also have a common factor in the numerator and those get canceled out, well, the function still doesn't exist for those x values that make the factor equal 0 because it would have made your denominator equal 0. So it doesn't give you a vertical asymptote in that point, or in that case, but what happens then is that you have a hole in the graph because your original function still can't exist at that x coordinate because it would have made your denominator equal to 0. So if you have common factors, and this is what this is saying up here, so s of x equals p of x over q of x. And if p and q have a common factor, you cancel out that common factor. Now, instead of that factor from the denominator giving you a vertical asymptote, the function still doesn't exist at that x value, so what you end up with is a hole at that x value. So just like an empty circle in your graph, right? A hole there where the function does not exist at that point. It's not a vertical asymptote, but it turns into a hole in the graph. Right? So since s is not defined for the value of x that makes the factor equal 0 because it would make the denominator equal 0, the graph has a hole at that x value. All right, so you can get holes in your graph in rational functions. So that's why it's important. And if you didn't watch the video that I did about all the steps of graphing a rational function, it's really important on that first step to factor your numerator and denominator. Right? And when you factor them, check to see if they have common factors. If they do have a common factor, that means you lose one of your vertical asymptotes, but then in its place you get a hole in the graph. All right, so it's something important that you need to check out when you're dealing with rational functions. All right, so I'm going to erase all this stuff up here now. I'm going to pause the recording, erase it, and then put up a couple of examples where we find holes in the graph and draw the graphs and see what that actually looks like. All right, so the example here that we're going to work with is s of x equals x minus 3 over x squared minus 3x. All right, so first thing I want to do, it looks like a rational function because I have a fraction, I have polynomials in the numerator and denominator. So the first thing I do is factor both my numerator and denominator if possible. Now, it's not possible to factor my numerator because that's just an x to the first power. So all I have there is an x minus 3, and that's it. There's nothing I can do to factor that. But in my denominator, the x squared minus 3x, those have a common factor of x. Right? So I can factor out that common factor of x, which leaves me with x minus 3. All right, now factoring, if you don't remember how to factor, you're not good at it, I have made a bunch of videos where I talk about all the different factoring methods, so you might want to check that out if you don't understand what I just did there. But that's what we call factoring out a common factor. All right, so normally when you factor your denominator, what you end up with is, to find your vertical asymptotes, you set your denominator equal to 0. So in this case, I would get, if I set each of those factors equal to 0, I would get x equals 0 and x equals 3, and that would give me two different vertical asymptotes. But in this case, since one of those factors matches the factor that's in the numerator, I can actually cancel that out, and that takes away that vertical asymptote at x equals 3. But what it leaves behind is going to be a hole in the graph at x equals 3. All right, so now I'm going to have a hole at x equals 3. Right, the x value that would make that factor equal 0, which normally would give me a vertical asymptote, now since that factor cancels out, gives me a hole in the graph. Right, hole in the graph. I hold up a little hole there, but you couldn't see it. And again, because this original function does not exist at x equals 3. Right, if I try to plug in x equals 3, I get 0 over 0, and I can't have a 0 in my denominator. So x equals 3 is not part of the domain of this s of x function. Right, it's not in the domain, so the graph cannot touch x equals 3. It does not exist there. Right? Normally that's a vertical asymptote for a rational function, but in this case it's a hole. So what this actually simplifies to, right, this s of x function, when the x minus 3's cancel out, I'm left with a 1 in the numerator and just that x in the denominator. Right? So my s of x function cancels to equal 1 over x. And 1 over x, if you haven't seen the videos that I did on parent functions and transformations of graphs, the graph of 1 over x is one of those graphs that you should know what that graph looks like. But in terms of the, graphing it like a rational function, well, where my denominator equals 0, is x equals 0. Right? So at x equals 0, this graph is going to have a vertical asymptote. Right? Just like we said here, we would have had vertical asymptotes at 0 and at positive 3, but we don't have that one at positive 3 because we got canceled out, right? Our x minus 3 factor got canceled out there. All right, so let me put some marks on here just so we can do the work we need to do to graph this. All right, so we have the vertical asymptote at 0. For the horizontal asymptote, the degree of my numerator is 1. The degree of my denominator is 1. The degree of my numerator is 0, right? Because we don't have an x in our numerator, so the degree of that is 0. When my denominator has a bigger degree than my numerator, my denominator is stronger, it's going to pull the graph down and give us a horizontal asymptote at y equals 0. Right? So the function 1 over x has one horizontal asymptote at y equals 0 along the x-axis. It has one vertical asymptote at x equals 0 along the y-axis. Right? And if you recall the graph of 1 over x, and again, it's one of the parent functions that you should just know what the graph of 1 over x looks like. It's down here in the third quadrant where it goes between those two asymptotes, and it's also up here in the first quadrant doing a similar thing between those asymptotes. All right, so that's what the graph of 1 over x looks like. But remember, we did not set out to graph 1 over x. We set out to graph x minus 3 over x squared minus 3x, and that graph has a hole at x equals 3. So I have to go here to x equals 3, and at that point at x equals 3, I have to put a hole in the graph. Right? And the coordinates of that point would be 3, 1/3. Right? If I plug in x equals 3 here, I get 1 over 3, which is 1/3. Right? So basically the graph of s of x equals x minus 3 over x squared minus 3x, it's exactly the same as the graph of 1 over x because that's what it simplifies to, except for that one point at 3, 1/3. Right? The graph is missing that one single point because my original function had that factor of x minus 3 in the denominator, so this graph this function does not exist at x equals 3. It's not part of the domain of that function, so we have to skip over that point when we draw the graph. Right, so that's what happens when we have holes in the graph. You factor your numerator and denominator. If you have a common factor, you cancel it out, but you don't forget about it, right? Whatever that factor was, whatever x value makes that factor equal 0, you're going to have a hole in the graph, and then just whatever it simplifies to, you graph that function. So I just graph the function of 1 over x, and then I just put the hole at x equals 3. All right, so that's one example of graphing a rational expression that has a hole in it. I'm going to pause the recording here, erase this one, and put up another example where we can kind of see a similar thing happening. All right, this next example, we've got t of x equals x to the third minus 2x squared over x minus 2. Right, so looks like a rational function. It looks like I'm going to have a vertical asymptote at x equals 2 because if I set my denominator equal to 0 and I solve it, I would get x equals 2. But before we just jump in and start doing the work with the vertical asymptote, we do have to factor this to make sure that that factor of x minus 2 doesn't cancel out with the numerator. So in my numerator, the x to the third minus 2x squared, once again, just like that last example, I have a common factor there, and that common factor is x squared. Right, so I can factor out an x squared, which would leave me with x minus 2, and then that matches my denominator of x minus 2. Right, so the factor will cancel out, and I get just x squared, right? X squared over 1, which just gives me x squared. So the graph of this t of x function is going to look a lot like the graph of x squared with one exception. Right? There's going to be a hole in the graph, and the hole in the graph is going to be at the x value that makes that factor that I canceled equal to 0. Right? So I'm going to have a hole at x equals positive 2. Right? Like we said, when we first looked at this, since that that x minus 2 is in the denominator, it looks like I'm going to have a vertical asymptote at x equals 2. Well, since that x equals 2 got canceled out, though, that takes away the vertical asymptote, but what it leaves behind is a hole in the graph at x equals 2. All right? So then, if we go ahead and sketch the graph of this function, all right, so each of those, I'm not going to put the numbers up there, but each of those dots or each of those little lines I put there should represent 1. All right, so I'm going to draw the graph of y equals x squared. And once again, going back to the parent functions and the transformations of graphs, you should know what the graph of y equals x squared looks like. If you don't, go back and look at the video that I did about the graphs of parent functions. So it goes to the point 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. And notice at the point 2, 4, I didn't put a dot there, I put an open circle, because this graph has to have a hole at x equals 2. Right, so for that point at x equals 2, it's not an actual point, it's a hole in the graph that I have to skip over as I draw the graph of this function. Right, so the graph of t of x equals x to the third minus 2x squared over x minus 2 looks just like the graph of y equals x squared, right, because it simplifies to equal x squared, except because of that x minus 2 that was originally in the denominator, I have a hole at x equals 2, right, which is the point 2, 4. Right? If you don't know where the y coordinate of that point is where you're going to have the hole, just take that x equals 2 and plug it into the simplified function. 2 squared gives me 4, so that gives me the x and the y coordinate of where I need to put that hole on the graph. All right, so that is graphing functions that look like rational functions, but it turns out that instead of having the vertical asymptotes, they actually just have a hole in the graph. So a lot of times those simplify to graphs of simpler things, like this one's just the graph of x squared, except for that hole that we have there. Right, so it's something to watch out for when you're dealing with rational functions. That's why you should always factor first before you start doing any other work, because if those factors cancel out, it kind of changes up what you have to deal with, having holes instead of vertical asymptotes.